Hello, I'm Rob van der Goot and today I will be presenting my paper titled We Need to Talk About Train Dev Test Splits. Now this is how we split our data in a standard machine learning setup. So the green bar here is the training data. This is usually the largest part of the data. And we use this to train our model. Then we have the orange part, which is the development or validation data, which we use to compare different versions of our model to each other. Then after we have found the best performing or most interesting version of our model, we can use the test data to estimate its performance on unseen data. So that's the red part in this figure. Now something has changed in this procedure since we started to use neural networks, because neural networks are often trained for multiple iterations and it's unclear which iteration produces the best model. So what we do in practice is we use the development data to get the performance of the model after each iteration, and then we pick the best model based on this performance on the development data. Now if we do this, we of course are overestimating our performance on the development data and are also overfitting our design decision on the development data. So people have started to notice this, and as a result they started to compare multiple versions of their model on the test data. So in practice they integrated the test data into the development phase, which is of course undesirable, because now we are overfitting our design decisions on the test data and we get an overly optimistic result on the test data. Now, I have some anecdotal evidence to show that this is the case, as well as some quantitative analysis. So first there is this tweet that mentions that if you compare your systems against previous NLP shared task results and you beat them by a small margin, don't forget that their systems were usually evaluated on truly unseen test sets. And this here sort of assumed that yours was not, right? So in many cases actually people don't keep their test set truly unseen up until they finalize their experiments. Also in the EMNLP call for paper, so this is the 2021 version, but in the 2020 version the same sentence occurs. They asked to report the corresponding validation performance for each reported test result. It's probably a better practice to compare all of our different varieties of our model on the development data and pick one of those, or maybe a few, and report the test result of that. So the other way around. Then to the quantitative analysis. I've collected 100 papers from 2010 and 2020 from ACL, one of our major conferences. And in these papers I've counted how many models were evaluated on the test set. Now these are the results. So these are box plots, so the quartiles are represented here, and on the y-axis you have the number of models evaluated on test data. So we can clearly see here that in 2020 much more models were evaluated on the test data. For example, in 2010, 50% of all papers were evaluating less than 4 models on the test data, whereas in 2020 this was only 25%. So in other words, now that the dev split is integrated into the training procedure, you have no data split left for comparing different versions of our models. Now from this problem definition, the solution follows easily. Because we don't have enough data splits left, we simply introduce another one, which we call the tune split. Now you can see it here in the last part of the figure, where we have a green bar for training, a yellow bar for tuning, so for the model picking, and we have the orange part, which is the dev set that we can use to compare different versions of our model to each other. One problem that arises is that now we have less data for training. This problem can easily be solved. So we can do our development with the train, the tune and the dev set. Once we have found our best performing or most interesting model, we can get the performance of this on the test data by training on the train and the concatenation of the train and the tune set and using the dev set for the model picking. So we can have a fair comparison to earlier models. Now, you can ask yourself, is this a new thing? No, not really actually. So in cross-lingual learning, sometimes the setup also led to a tune set, just without this name. So if in our source language we have a train and a development data, and in the target language we also have a development set. And in practice people often use the source language train data to train their model, the source language dev data for model picking, and then compare different versions of the model on the target language development set. So in practice, the source language dev set became what I now call a tune set. Furthermore, in machine translation there is something called a dev test set, because in machine translation multiple test sets were created for shared tasks, and this was sometimes used as a tune set as well. Furthermore, In shared tasks, the test split is enforced to be only used a few times, because you're not allowed to submit an infinite number of models. And also, some online benchmarks keep the test set secret. In both of these setups, people often simply use the dev set for model picking as well as hyperparameter tuning, which is suboptimal. And in other work, Chen and Ritter recently proposed other model picking strategies that don't require a dev or a tune set. So in this setup, you can safely use the dev set to compare different versions of your model. To test the effectiveness of the tune split, I did some fine-tuning experiments based on the universal dependencies data. I took the subset of tree banks selected by Smith et al. 2018, which is based on annotation quality and language variety. And I compared two different parsers to each other, namely the matchn parser, a deep Bayesian transformer-based parser, and the UU parser, which is a ByLSTM shift-reduced parser. I compared two setups, the original setup where the dev set is used for model picking, and the newly proposed setup where the tune set is used. I concatenated the train and the dev data, and from this I took the last 3,000 sentences and used 1,000 of these for tune, 1,000 for dev, 1,000 for test, and the rest was considered to be training data. This is shown in the graph here, where on the x-axis we have the total dataset size, and on the y-axis we have the size for each split. You can see that the tune and the dev, the red and the blue line here, are constant, and the train set increases. The train split size increases as the dataset becomes larger. And there's one big flaw here that we realized when we were doing more experiments with the tune split, is that small datasets are not considered. So we redesigned this splits in what I consider to be a better alternative, where for datasets smaller than 3,000 sentences, we use 25% for tune and dev, the rest for train, and for datasets larger than 3,000 sentences, we use 750 for tune and dev, and the rest is train. As you can see in the graph here. So here we can see that also small datasets can be used. Then to the results. So in this table we have our results, where on each row we have a tree bank, and in the columns we have the two different parsers. First, we report the amount of different hyperparameters found when finding the optimal model. And we can see that in many setups the hyperparameters are at least slightly different. Then we can also see the results when not using a tune set, here the minus t, and when using the tune set, here the plus t. And we can see that the differences are very small. We did statistical significance testing with a random bootstrap test and found that none of these results were significantly different. This is not necessarily a negative result, as with our new setup we achieve on-par performance, and we can use the dev set for qualitative analysis, which was not possible before. A reviewer also suggested that a smaller training size might show different results, and these experiments are unfortunately still running due to computational and time limitations. Thanks for your attention.